That's actually the first time I do this presentation outside of the automotive ecosystem that you may know that it's maybe quite close because maybe people are not speaking to the other people in the industry. I'm actually used as a micromechatronics engineer, so I don't have a specific background of software engineering, but I've done software development since I was 12 years old, starting with PHP, don't blame me, and mostly volunteering in non-profit organizations around climate data science and popularizing the issue of climate change around the citizens. Then I was mostly working in the cybersecurity industry, so in the defense agencies in France, and also in the medical industry, and now I'm working in the automotive industry at Renault/Ampere, which is quite the same company now. So you can see that's quite regulated industries, and regulated industry have some interesting characteristics when they are dealing with software development that I will highlight a bit during this presentation. But first, let me show you a small video. So I know this is not a Renault, right? This is a Tesla. So this is actually some of the contests. So this was extracted from the Pound-to-Own contest, where French security researchers from Synactive were able to actually hack a Tesla using the Wi-Fi connectivity of the car. So this is something that we see often, this kind of vulnerability. Here it's not really safety critical because it's just opening the frunk and making the wipers wipe. But if you can propagate the attack further, it could actually trigger some safety-related consequences, like not braking when seeing a pedestrian or doing emergency braking on the highway at full speed. So actually, when analyzing this kind of attack, that we do it often, we understood that Rust could have prevented this, actually. And I'm not joking, and I will not be doing any jokes on Rust on cars, not more, because I already did a lot of them. And by the way, I showed a video of a Tesla, because Tesla is actively involved in doing this kind of research and demonstration of security issues. And kudos to them and Synactive, because they do really great work in this industry. And this is the fix of this vulnerability that you've just seen. So the hack of this Tesla was actually, part of the vulnerability chains was actually bad management of a string in the code of a HTTP server somewhere in the car. So this is comically simple fix that you can have in this kind of attack chain, which here is as a consequence of opening the frunk and making the wipers wipe, but could have severe safety consequences for other use cases in the car. So starting from that, it's a simple statement. Now the automotive industry is a bit redefining the way it's working with software. And automotive manufacturers tend to have more and more responsibility over the software they integrate into their cars. So for two different reasons. First is some market redefinition, thanks to the concept, the marketing concept of the software-defined vehicle, where we take more and more responsibility and design our own software development instead of buying from other suppliers. And also because of regulations, which is a great thing, of having more control of what code actually runs into your car and having more control over the quality of this code. And having more and more software, so roughly a few dozen million lines of code in a regular car now, means you have more bugs and then maybe more vulnerabilities because this software is more and more connected to the cloud, connected to the internet. So, and collectively, as an industry, we still somehow fail managing all those attacks and those vulnerability surfaces, and we see that in the media very often. Of course, we can think that Rust and its reliability and quality by design is a great idea for car makers. This is a simple statement, but in our big, large legacy corporations, it could be really difficult to just say it's better, it has intrinsic quality. It's something which is not enough to really trigger changes in such industries. So here is some of the stories that I could tell you about how to manage integrating Rust into those kind of companies where it might be more difficult to integrate Rust than in a startup or in a tech company. So I will take you an example. So I'm working as a cybersecurity architect, so my job is to basically not write software, but make sure that all the things that we integrate into the car make it safe. And when analyzing the cybersecurity measures in the car, we can see that often it strictly limits what we can do in the car. So you cannot communicate like you want, you cannot integrate the protocols you want, you cannot do whatever you want, and it makes the overall car more expensive and more complex. So just take an example. This is a really simplified architecture of what's a car today. So cars that you can see on the road today are basically a layered architecture or a tiered architecture where you try to separate what is the exposed area. So the exposed area is the right one, where you can have, for example, an Android infotainment system where you can download apps and you can easily have exposed interfaces like the internet, like the Wi-Fi connectivity. And on the leftmost side, you have the safety critical area where you have actually the ECUs. So ECU is basically a computer running the safety critical code, which is, for example, able to detect pedestrians on the street, but also do emergency braking of your car. So often you have this interface area where you are trying to mitigate the risk of interfacing the exposed world to the safety critical world. And often this is communicating using, for the rightmost side, some simple UDP-based Ethernet protocols where you are doing some some inspection of what's happening in the network and access control on the network. And on the left side, some maybe simpler CAN-based protocols or Ethernet protocols in the case of Renault. So you have quite a low attack surface on the interfaces. And somehow, when you want to make those two worlds discuss, so rightmost world is the exposed zone, so Android, Linux system directly connected to the cloud, and leftmost one is the safety critical functions. You want to communicate between those two worlds. So let's, for example, see that you want to interface it using some very old protocols like you can see in the automotive industry, and some of them, one example that we can have is some IP protocol, which is based on simple UDP serialization stuff, and you want those worlds to be able to communicate. And one of the risks that people see when doing the security analysis of such architectures is that you have actually vulnerable code in the communication stacks and applications that use those communication stacks on this safety part. So this is the main risk that we see when analyzing the safety of this kind of architecture. And of course, the risk is that if an attacker is able to take control over this vulnerable code in those communication libraries, it could actually be able to trigger safety critical functions. And the overall impact of that could be, for example, you are driving on the highway full speed and you have an emergency braking and you don't know why. So this is the kind of attack surface that is considered here. So to mitigate this risk, usually, car manufacturers implement some kind of proxy or gateway approach where you try to isolate this rightmost world to the leftmost world using techniques such as packet inspection, packet deconstruction and reconstruction, inspecting all the layer stack, inspecting the payloads and making sure that whoever communicates from one world to the other world is actually able to do that, like checking the MAC addresses, IP addresses. I'm not talking about cryptography here, but some basic systems like that. And that's how it's used to work in traditional cars. And when you have more complex protocols that you can imagine, like mutual TLS with more complex TCP-based protocols or more complex stacks over UDP, it's often just forbidden, so you could not do that anymore. And this costs a lot of money because each time you want to have a new protocol integrated between the two different environments, you need to put a lot of money to actually design the code that is doing this proxy function, but also validating the whole system. And when you are integrating this kind of architecture, the complexity rises, and then it's more complicated, and you have bugs to manage and so on. So it costs a lot, basically. So it's not really scalable. And the impact of that is that, well, you are not flexible, and you can't do anything you want when communicating from one part of the other part of the car. And if you want to transfer data from one side of the world to the other side of the world, you basically cannot do that. So developers are frustrated, architects are frustrated, and it's quite complex. And of course, you have, as I said before, cost and delays impact because that costs multi-million euros to design such proxies inside a car. And it's wasting resources. So you often dedicate full cores to do this packet inspection, deconstruction, reconstruction. So it's wasting energy, it's wasting performance that you have on your car computers. And as I said before, if you want to integrate more complex protocols that are, for example, doing end-to-end confidentiality, like a mutual TLS, you can't do that anymore because it's breaking the end-to-end security properties, acting as like a single point of failure or man in the middle. And of course, this proxy approach still has vulnerabilities possible, so this is not bulletproof. So first thing is, what if we could remove this complexity, so removing the proxies and gateways? First, let me take back a little bit to what is the overall software development picture in traditional automotive companies, where you have your initial design and you have some security by design rules, like system rules, like saying you cannot use this protocol because we think it's too complicated. You cannot communicate between this infotainment system to this LiDAR system because it's too risky. Such kind of rules that we implement in the systems. And then you have your development processes with regular C or C++ code and having restrictions, a lot of restrictions in the code that you develop, like the MISRA rules for those who know those rules, and also compilers restrictions, like using proprietary compilers that were stamped by some organization. And then you have your post-development techniques with expensive static analysis tools, dynamic analysis tools that you implement in your CI/CD. And somehow you could also have some fast cycle pen testing and bug bounties, like we've seen with the Tesla before, and trying to improve continuously this situation. And we can even extend it to like certifications, like common criteria certification or formal proofing, so mathematical proofing of the correct behavior of your software. And you still have some issues at the end when the car is on the road, because all of those layers of security have their own internal issues. And one of those issues are memory safety, and you're all aware of that. And this is one of the most important amount of vulnerabilities that we see usually when analyzing the traditional attack surfaces that we see on car attacks, like I've shown before. And of course, Rust is an opportunity for that. So I'm sure you are well aware of that, and you still have the logic vulnerabilities possible, like if you have a client-server communication, and the server is not checking the authentication of the client, for example, you have a logic vulnerability. But thankfully, the test framework of Rust is great, so we are also able to limit those logical vulnerabilities somehow. And of course, you have the inherent benefits of Rust, and I know that there is a presentation just after that we'll talk maybe a little bit more about that from Lars, and that when you are a good C or C++ developer in the industry, you need like decades of experience to be able to achieve some good quality software, and you still will make some memory management mistake. Where you are a newbie Rust developer and you just learned like a few months ago, you will be catched by the compiler even before making the same mistakes. So this somehow is also helpful in some companies which are trying to reduce their cost by outsourcing or by having more junior developers. And that's a reality. Those facts may seem trivial to you. These architectures, these network protocols may seem very trivial to you, but believe me, in large legacy companies that are not from the tech industry, which are not startups, it's really, really complicated, and it's a deal-breaker change. So remember what I told to you about the need for proxy or gateways to make those different worlds communicate, fearing of memory safety vulnerabilities? So what we are trying to implement in the Renault architecture is actually to say that if we can have memory safety guarantees on the protocol stacks, then we won't need anymore this complexity of having a proxy or gateway. So basically, implementing your protocol stacks and the applications that communicate using those protocol stacks using Rust. So that's the basic idea around that. And making that, you could actually say that if you use Rust, you're allowed to do more things. You can communicate more freely in the architecture than before, at a lower cost, because you don't need to design those proxies and gateways which are complicated, expensive, and somehow overkill. And actually reducing technical debt, because you don't have to have those complex rules, you don't have to have those specific development and specific CPU cores that are allocated to doing this kind of checks in the car architecture. And recently, Google Chrome was saying that it was able to move its QR code generator out of the sandboxing area by using memory-safe libraries written in Rust. And it was interesting to see that by using this memory safety approach, we are actually able to reduce system complexity. So we made Rust mandatory for some specific part of the software, saying if you use Rust with some rules that we've defined, which are really simple, you are actually allowed to do more things than before. And then the consequences of that is that it will naturally propagate in the remaining of the infrastructure because of the interfaces, because of course you need to interface through Rust systems, so you are maybe likely to also propagate this using your other software components. And also because when developers start doing Rust, they actually like it, of course, and then it actually propagates it naturally in the organization. And what we see also is that time to market is actually able to improve using Rust, like 20% less time to market because of the properties of the ecosystem and the capabilities of the cargo ecosystem and all the tools that we have around the Rust ecosystem. And one topic that we already discussed today is control over the software supply chain. So we talked about software, bill of materials, and that's also something important for regulation. And this means that the cybersecurity people are like happier to have more control over what software is actually running exactly on the platform. And somehow in legacy companies, so Renault has 200 years of legacy as a company, it's somehow Rust is trying to bridge the gap between perceived security and actual security. Because when you are talking to executive in big companies, somehow the perceived security is important, and the sense of actual security might not exactly be the sense of actual security that you have as developers. And somehow I found out that Rust is able to bridge that gap and convince both kind of people of these actual properties or quality properties of the Rust ecosystem. So at Ampere Renault, we think that using those distributed security, so basically improving the security guarantees of the code everywhere in the architecture is a way forward. So no need to have those black boxes doing inspection and doing whatever complicated stuff to try to have a sense of security. We actually need to put in place distributed security. So we are already integrating Rust as part of our development processes, and we already use it. So for cars that will be shipped in 2 years, I think, from now, in some security software. So we are doing some heavy packet processing in a common criteria certified environment in Rust. And that's a software component that we have seen having a time to market divided thanks to using Rust instead of traditional C++ plus the usual rules of the automotive industry. And we are also starting to use it for driver assistance systems, so ADAS systems, where we have non-safety use case for now, and we are planning to run some safety proof of concepts for up to ASIL-B. So ASIL is a safety classification that you may have known for those who have seen the workshop from Ferrous Systems, and we are trying proof of concept for later years on safety critical systems. And we also use it because the goal is not to rewrite everything in Rust. You know? We have too much legacy and too much systems to be able to actually propagate Rust everywhere. But however, we can see some particular areas of interest where it's useful to harden the legacy code which is executed on the platform. For example, when you are doing processing structures coming from the untrusted networks for cryptography purposes, you absolutely want this code to be sound and memory safe. And that's also a strong requirement that we will have in the new SDV operating system that we are developing with Google, because as you may have seen in the media, Renault and Google have partnered to design a new operating system for ECUs, so not only the infotainment system, so the screens that you can see on the car, but also for internal electronic control units that are doing more automotive-related software. And this new operating system will actually use Rust massively and use it as a by design, as a by default programming language for the APIs that are used to communicate with the other systems. So, as I said before, I think using Rust could clearly be useful for the automotive community. However, we need to find like a killer feature or a killer area where it could actually convince a big corporation or a big company to make the switch. Because saying it's better or saying it has inherent properties, qualities, and so on is not sufficient somehow, and it could not convince enough people to try to make this switch. So we achieved it using identifying some cybersecurity critical use cases and making them mandatory to use Rust. I say mandatory to use Rust. And then using the legacy code, so still using the legacy code because we have a lot of legacy from C, C++, or even assembly, which is integrated into that. And the goal is not to rewrite this legacy because it's like too much work to do to deliver actually the cars. So we need to live with those legacy libraries and legacy features. And this is where it's actually interesting and important to define the boundaries of what we actually rewrite in Rust, preferably in safe Rust, but using unsafe is not a bad thing. And also closely controlling which part is mostly exposed and which part is less exposed. So that's actually a job of cybersecurity engineers to try to define those boundaries and see what we could rewrite in Rust and what we could keep as a legacy software. So as I said before, in internal developments that we've done, that will be shipped in a few years in newest Renault cars, we observed up to 20% faster time to market to deliver the actual software components using Rust, compared to traditional approaches, by the environment which actually helps you doing better work. And what's important to note also is that we also have the discussion about training people. So we have a lot of people which are used to work with C or C++, somehow older versions of C and C++, and we had a lot of training, internal training session, external training sessions, thanks to external companies. Like 100 to 200 people were trained last year, and what we observed is that they are quickly up to speed, basically. They like it, and they are quickly up to speed. So this is why we think that by starting slowly to have touches of Rust, making slowly mandatory touches of Rust in the architecture, we are actually able to increase the incentive to use Rust for our internal developers, but also increase the incentive for all our ecosystem. So ecosystem is all the suppliers that actually write code, which is integrated in automotive platforms. So this goes from communication stacks, from low-level firmware that we could see on the cars to BSP or hypervisors, for example. And this is what we have some interesting discussion also. So here I talked most about higher-level software. So mostly in Linux-based environments where you have most freedom over what you can do and use the standard library and so on. And we also see some other areas where we would like to see more oxidation of the software stacks. And then I will dig a little bit into that, and I will be more have a more comprehensive presentation on that at Rust Netherlands in a few months, is how it could be helpful for system-on-chip components. So as I said, cars nowadays look like that. So every blue box is a box, actually, which somehow in the earliest day were sourced from different suppliers, and it was seen as a black box. We don't know what's inside. So here's the braking ECU, here's the LiDAR ECU, here's the infotainment ECU. We plug together, and it works, and it's a car. So basically, that was the way car companies were working a few years ago. But so each one is like its own processor or microcontroller running one or few operating systems and connected together using simple protocols and Ethernet or CAN networks. And the world is a bit changing because now the trend is to have more beefy CPUs with many multiple cores, somehow coming from the server world, so mostly what you could find in the data center. And you integrate that in your car, and you hope that using some hypervisor and those multiple cores, you can do everything that your car did before in several different ECUs in a single one, modulo the thermal dissipation, which is some issue. And that's basically what we can see. So the different security zones that you've seen before, so green, yellow, and red, are actually now in the same system on chip. So in the same big silicon area where you have different virtual machines or different clusters, CPU clusters, blocks, integrated together, and somehow sharing some low-level components of the system on chip. So hypervisor first, which is a higher level, the cores and the clusters, and also some various IPs that you can find in system on chip. So if you look like of what's inside a system on chip, or a typical Raspberry Pi and so on, you have some GPU controller, neural network controller, some DSP for mathematics operations, some networks accelerator IPs, some cryptographic accelerators. What could see that crypto IPs could be secure elements or strongbox in the Android world, or some proprietary IPs, proprietary management IPs that semiconductor companies said that, believe me, it's secure. It's there, but it's secure. And some backdoor IPs, you can find whatever. So there have been a lot of discussion around architectures of system on chip, and open hardware is also a different concern, but somehow it revolves around that. And everything is connected through internal buses of the system on chip. And you have your different environments, so the Android ecosystem where you can download your own APKs or something like that. And you have the happily emergency braking function somewhere in this kind of real-time operating system somewhere on the system with internal bus that nobody really knows exactly how it's connected because you need deeply non-disclosure agreements and some confidentiality stuff for you seeing actually what's inside the system on chip. So this is what the future looks like, according to some people in the industry. We are not quite agreeing with everything, but anyway, you clearly see that now the attack surface is everywhere. And if you have every single of those blocks is actually running some specific microcontroller core, like Cortex-M, and running its own firmware. So every of these light blue blocks is actually running its own small pieces of firmware and having a lot of privileges in the overall system on chip. This means that if you have like a memory safety vulnerability in the cryptographic IP, for example, and the Android system is somehow able to trigger this memory safety vulnerability on the cryptographic IP core, this means that now your full-fledged infotainment Android system can send safety braking commands to the braking actuators of the car and actually be able to make your car brake, do emergency braking on the highway at full speed. So you see now that this kind of ecosystem means that you could not have like before. So before you have simple links which allowed you to somehow have a lot of control over what's happening between the different worlds, and now you don't have this anymore. This means that distributed security and having more trust on the quality of the software components that are below is very important. So this means that what we did traditionally with an exhaustive, centralized control and inspection of all those data flows in the car will be more expensive and paid for most impacting because the data flows are increasing. Before it was like 10 megabits per second. Now it's 2.5 gigabits per second of data transiting from those worlds. And it will be like very fragile because you need to do this more in more complex network stacks and even be very complex or impossible. I was talking about end-to-end encryption for different use cases. If you are doing end-to-end encryption, you cannot inspect anymore the data that's inside the payloads. So what can we do better in this context? Today, to try to mitigate this risk, what we ask is security certifications. So like when you are integrating a system on chip with two different areas, different security areas on the same system on chip, you ask for security certifications of the common shared components. So for example, certifying the hypervisor. So you have an hypervisor. I want to guarantee that the different virtual machines are actually not able to see what each other is doing and to interfere with the functioning of the other virtual machine, including the drivers when sharing some peripherals of the system on chip. This is really complex, and somehow security certifications, like the common criteria for those who know, are quite fragile, very bureaucratic, and a lot expensive. So this is not really convenient, but asking for guarantees is a complex stuff, and we actually find this way as the lowest, as the best idea to try to convince the SoC manufacturers that there is something to deal with. What we may ask for tomorrow is, as I said, for those lower level blocks of the system on chips, we need more memory safety in those lower level components. So I'm talking about hypervisors and their drivers, the firmware blobs that are loaded to basically make those IPs work in the system on chips are really some areas of work where we would benefit from more openness, more memory safety, and also somehow reproducible builds and attestation of the code that is actually running, but this is for another topic. Actually, one interest that we see to that also is that writing this kind of code using Rust is also a benefit for achieving formal proofing, so mathematical proofs that your software is actually sound and acting correctly, and for safety certification. So when we want to do this kind of architecture for a car, you need to have some safety certification available, and Rust actually helps doing that because of the borrow checker and because of the properties of the compiler itself. So see also the Frédéric system talks about that. One issue that we run into is managing the supply chain. So when you are doing Rust, you have a wonderful ecosystem of crates and existing crates that you can use in your project. And somehow, let's not do like NPM did, and somehow having supply chain attacks. So meaning that when you are integrating this crate from whatever open source or proprietary contributor, you want this crate to not be able to propagate attacks through your car in the components that are using this crate. So there have been great work done by the Rust Foundation to address this issue and to try to do risk analysis of the crate ecosystem. We also internally are defining some rules that we would like to publish and work with the ecosystem on what kind of rules we could have to manage this supply chain attack issue, or basically how do we make sure that the dependencies that we integrate into our cars are actually safe and safe for a long time. And I think the industry also have a role to play helping doing managing this topic. As I said before, we are slowly using Rust and making Rust mandatory for non-safety critical components, so higher level components that are not ASIL tagged. And we are starting slowly to want to use Rust for safety critical applications, mostly for driver assistance systems, where you have to write complex code that is basically doing like optical flow tracking or trying to use data from LiDARs or from cameras. And this is complex code that you want to benefit of having a great programming language. And so that's more for better code behavior, better soundness, and not more for cyber properties. So that's another area of concern. We need for that to define like what kind of formal guarantees we have on memory safety, and there have been a lot of work done already on that. And also, and I get back to this sense of perceived security, how do we map that to the usual way we did things before? So for example, the MISRA rules are pretty common in the automotive industry, so defining a few hundred of rules saying you cannot do that in C++, and 70% of them are useless for Rust because the compiler already takes care of that. But the industry wants us to basically write it and be sure that those MISRA rules are actually not useful and making the map between the old way of doing stuff and the new way of what we could do with Rust. And other stuff that we are trying to achieve as well is pushing this memory safety towards our suppliers, and they are numerous. So I told you about hypervisors, where most of the concern is actually more on the drivers. So when you are sharing a GPU, when you are sharing flash memory, when you are sharing different devices of a system on chip or a processor, you want this to be actually safe when using the drivers. And we have seen a lot of attacks in this kind of areas in the past. As said before, all those proprietary firmware blobs into the system on chip or the processor would actually also benefit for the same reason, because they are shared among different exposure environments, so we actually would benefit. And we have seen also attacks in the past, for example, in boot sequences of automotive semiconductors, where boot sequences are doing very complex cryptography on untrusted data coming from the flash storage, and you absolutely want that to be memory safe. And also for all kind of other exposed components, from whatever data you receive from whatever source which is not trusted, you want to think about memory safety twice. Another important area, I think, is how do we improve the relationship between big corporations used to proprietary stuff and the open source community. And this is also making the map with what we discussed before about RustSec and vulnerability management, and how do we use, for example, CREV system to actually propagate trust in the Crates ecosystem. How do we upstream changes? How do we manage licensing between those different actors? This is not an easy task, but I think the industry has also a role to play by defining how to work correctly with the contributors that are managing the crates that we are using. So it is not something great to see that, for example, you can receive an email from whatever automotive company, and you are a volunteer doing open source development, and the people from the automotive company are saying, please fix this vulnerability as soon as possible. This is not something that we can imagine working in the future. So, few conclusion bullet points, I guess. So we found out that Rust is actually some lowest hanging fruit for having cheaper, more simple, and secure solutions for the automotive industry, which actually improves both time to market and overall satisfaction. So when I say satisfaction, we're actually able to satisfy the cybersecurity people, the higher level executives, and also the developers, and as well the users that actually use the car. We started demonstrating that it's actually effective, so reducing time to market, improving security, and we will spread it more and more in our roadmaps, in the software roadmaps, with a strategy of Rust by default for new developments. And the remaining of the automotive community, because we are only car makers, we are not the overall automotive community, needs to actually embrace this as an opportunity. Most people see that as fearing this new ecosystem that is here now, and we think that it's actually an opportunity. And we are often, and I do different conferences in the automotive industry to try to train people understanding Rust and understanding the characteristic of Rust and how it could actually be helpful. And the more we are to use it, of course, the more it will be used to improve the overall ecosystem. And as I said often, because I always have this question for when talking to automotive colleagues, is that, of course, Rust does not solve everything. So you still have the logical vulnerabilities. We still have cryptography to be made correctly. Correct cryptography is important. Defense in depth, like isolation, sandboxing, virtual machines, SO Linux, whatever you have, and integration, testing, security by design, and having simple architectures and holistic approach of security are really complementary solutions. So it's not saying Rust solves everything and Rust is the solution to this specific problem and to all problems, but it's important to keep in mind that all that was discussed before. So there is an interesting talk just before me around what quality we could have more than what Rust provides by default, and all of this is really important to make sure that we do great quality actually software. So I'd be glad to answer any question that you might have. I know that this may not be easy to understand all this automotive-specific stuff, but I will be really glad to have your feedback and understand any of your questions. Thank you.